Hey everybody, we're back for another live stream of how long is it going to take to make some puzzle games. So last time we were working on trying to wire up a system so that all of our agents can collaborate together in worktrees, and it was going pretty good. I had a personal best of 3 consecutive mayor sessions, I think, give or take, that basically didn't take input from me, handed off to each other, and just continued working on the big pile of work. And as I said last time, this is kind of the ideal if you want to be the CEO, get out of the way of your engineering department, only be troubled if something rises to your level, essentially. And I think that these mayors have really been trying to do that. Um, so last time we were saying, hey, we've got, we've pushed our backups essentially to our private Git repositories, and I did some GitHub auth, so it should be able to do its own thing now. And we're seeing where it got to from there. Cool. The remaining piece is the heavy live part. Putting all of the running agents onto this new pin, meaning do your work in work trees from now on, and then do a smoke test with all of them. Formulas using graph-only constructs must do this thing. This is like an implementation detail that I'm not aware of. We would have done a gclint that could have caught it. Okay, so it sounds like we're using some features that are newer. The candidate is live at the config layer. Okay, everything's reversible. I mean, even if we merge this into main, we could reverse that. We could go backward, but we're at a risk. We haven't talked about this very much, but let's talk. Let's do a little soapbox time and talk about one-way doors. So the idea of a one-way door is that when you go forward with a deployment or a software change or something like that, that is hard to reverse or even impossible to reverse, right? Like perhaps for regulatory reasons, once you modify your database schema and start storing records in it, you can never unstore them that way. You have to keep the records forever. And so adding on to your database schema is kind of a one-way door, right? And it's like it can always grow, but it can never shrink and it can never break its old contract. And you have to support those old records long into the future, maybe forever. And so I've worked at places where that was the case. Like you're a rocket company and you need to store your records of the rocket forever, or you're a financial company and you need to store your transaction records for a really long time for anti-money laundering or other regulatory reasons, something like that. And so that meant that you had to be able to record everything for auditability far into the future. And whatever additions you made would have to be supported kind of forever. And that's something that we see too when we're creating backwards compatible services. Uh, Adding a new public API is kind of a one-way door. If you're like, I'm never going to break my customers, I need to support this API forever. It needs to survive certain modifications of the architecture, or it needs to stay relevant for as long as we continue making records or manipulating transactions of a certain kind. And so those are very heavyweight kind of steps where you are very careful about how you expand your API or you expand your data model because it's really difficult to undo that stuff. Uh, the other thing about one-way doors, I guess, is that once you have crossed through that one-way door, people start building on top of that. And it becomes that much harder to unwind not only your own thing, but also all of the things that depended on that thing. So we have sort of like hard one-way doors and soft one-way doors if you want. Like a soft one-way door or like a 1.5-way door is, yeah, we could unwind this. Uh, it would just get more expensive over time to do that. It's not impossible, like rip up the company and start over, impossible, but it is expensive. Like, why did you do that? Expensive. So here we're probably talking more about like 1.5-way doors. When it says that everything's reversible and nothing is merged, right? Once we merge all of these changes to build in work trees and that kind of thing, we can reverse that. We can revert back to sort of a hopefully we won't interfere with each other world that we were in before. And that is mostly a behavior change. But we've made a lot of different changes in this branch to make this whole thing possible. Like we've wired in worktree configuration, we've ordered many of our different formulas to pay attention to worktrees, to acquire a lease before you start working on a collaborative project, all that kind of stuff. And so unwinding it is like, because we've scribbled that fact or we've used that fact in so many different places, right? It would be expensive to go and unwind it, cause bugs potentially. So yeah, we can sort of think of this as when it says all reversible, it's kind of talking about two-way door. And it says we haven't merged anything. It's saying, well, after we do merge, now we're not talking about something that's so reversible anymore. These formulas have never run at runtime. It's a full prototype generation that's expensive in many agent sessions. I think that's fair. Any of the dispatch sessions might need my Claude auth to stay fresh. Okay, fair. All right. Uh, sure. We don't have to do the full. So we're going to get signal from this test, right? Like if this thing doesn't work, then we're going to, pull back and figure out what worked. And so we're sort of shaking out this whole approach before we just do this big bang kind of integration test. So I'm with this plan. All right, so it's going to take over and do that, I think, and then we shall see. I really did like this Yagi to Okami uh, puzzle, Goats and Wolves. It was a lot of fun once we figured out what was going, and I did feel it was very thematic and interesting, and that's definitely something we want to take into our future puzzle making. Um, we finished Yajidin very fast. Yosinabe, what's this? Move all the circles horizontally or vertically into a gray region. The trajectories of circles must not cross each other. They must not cross a circle, but they might cross a gray region. That makes sense. Like There's a lot of things that we do to make it easy to do these puzzles with a pencil and paper. And we don't require erasure, we don't require scribbling over other things, that kind of stuff. At the end of all moves, the sum of the circled numbers must equal the number in the gray region. For gray regions without a number, the sum is not known. Every gray region must get at least one circled number. All right. I think that makes sense. Trajectories must not cross each other. So we can't cross the two lines. They can't go in circles. They might cross a gray region, but then nothing else is going to cross in that square. All right. This does seem a little familiar to other puzzles that we've done. And that's not totally surprising. Like, I think if there's one thing that we're taking away from all of this, it's that there's been a lot of repetition over time of different mechanics, different combinations, that kind of thing. And so all of this stuff that we're seeing should start to feel familiar, you know. Hmm. I don't know if we saw a rule for the reverse. Is it true that every circle has to go somewhere? All the circles have to end up in gray regions? Yeah, move all the circles without turning into a gray region. Okay. So like we need to find a home for this 5. We can't cross other circles. So going down to here is like the dead end in this direction. And going over to here is like the dead end in this direction. Now look at the homes that we could put this 5 in. It would go into this 4 or this 4. It's too big for those. It could go into this 5 or it could go into this 2. So there's actually only one place it can go, which is right here. I'm just going to put a little X here so that when we see an X, we'll look back along the line and we'll see that there's 5 there. And this region is satisfied too. Now look, this region, does every region need to have a circle? I think that we figured that out, right? That's one of the, yep. It's one of the rules. And so we can tell that the only circle that left that can get into this region, because this forms a wall, right? This line we drew is this 4 right here. Oops. It'd be nice not to cover up the number. There we go. Just want to be a little careful about that. We've got to get something into this region, and due to the walls in place, this is the only way to get there. We've got to get something into this gray region, and the only one that's accessible is this 2 right here. We've got to finish off this gray region, and so we need a 2 to go into the exact one cell that we have available. So these 1s will not do. It's got to be this 2 down here. Forgive my not straight line, actually. Man, I don't know, I'm having trouble with this. That's slightly better, but I got to figure out how to get the pen interface onto this computer. Okay, we've sort of hemmed in this 1, but it can still go to either this 1 or this 3 region. So it's a little undecided. We've got to fill in this 4 region, and the only ones that can reach it are this 3, this 4, and this 2. So because there's no way to sum to 4 except by this, we have to choose this 4. And essentially this square right here is never going to get used. It's sort of a dead end for everybody. Okay, we could do kind of the same analysis on this 3 region. The only ones that can access this 3 region now are this one, this 4, and this one. So the only way to sum to 3 with those is to use the ones. We'll do that now. There we go. We need to get a 1 into this region. We can't use this 2, and we got to use this 1. It's the only one that's left to do the job. That was a pretty straight line. This 2 region is a little, or this 2 ball is a little hemmed in, but it can go to either this region or this one down at the bottom. But the problem is if we took it down to the bottom, then this region would get blocked out. So that would violate our rule that we need to have a ball. In every region needs a ball. So we're going to use this one. It's the only thing, useful thing we can do with this ball. Similarly, this 4 is very hemmed in now, and the only useful thing we can do with this ball is go right here. Let's see. Adding to 2, the only ones that can access this now, these are used up. They're kind of forming walls. We've got this 2 and we've got this 1. So in order to get to this sum, we got to use the 2. This 1 has no place left to go but here. This 3 has no place left to go but here. There we go. All right, what's left? We've got to get to 2 in this one. The only accessible balls are this 1 and this 1. So in they go. We've got no way for any ball to get to this square, so we've got to get to this one. And this one has to go there. If it passed through, then no other ball could reach this region. And finally, we've got this region that needs a friend. There we go. Kind of fun. It was kind of like canned, but it was sort of fun to see everyone making friends, going places. And we've sort of put everything in its right place. That's kind of fun. So even though it's very abstract, yeah, I found it kind of interesting. How are we doing? It's still working. So it's done. I wasn't time stamping the clock, but maybe 10 minutes of work all by itself. We're coming near the end of our Nikori puzzles in the Yanko database. So we did a set of the Nikori puzzles from the Nikori website in English, and then this list had some more that weren't published on the English side of the website. I think we did Choco Banana before. Double chocolate. Oh my gosh. If we recognize one of these, like Hashi wo Kakero, we're not going to do it again, but there are some new ones I can see. So why don't we just go through these one by one. Chained blocks. Chaimburo. Blacken some cells. The black cells are orthogonally connected areas. Each has exactly one cell with a number or question mark. I guess there are no question marks in our example grid. The number indicates the number of black cells. The question indicates any number. Black areas that touch at grid dots form a chain. Every black area must be part of a chain. Not all the same chain, but some chain. So they need to have at least one neighbor. The black areas of a chain must differ in size and shape, with rotated or mirrored shapes considered the same. That's cool. All right. So we can't have two of the same polyomino together. Oh, chained blocks. Let's just use the Japanese name. Okay, exactly one. So this can't be. This has to be. We actually can't. So the ones that this polyomino can't reach, it can't use this square or this square or this square. So it has to use these to get to exactly 4. And then once we've finished a polyomino, we know that none of these are connected. And now that these are chained together, we know that neither of these can form this polyomino T shape. Here we can say these ones are connected. All right. We definitely have to go this way next. If we did go this way, then we'd be forced into we can't use these ones and we'd be forced into a T shape. So we can't go that way. We go this way, and then we have to go this way. There was no other choice there. All right, and so we have this L shape chained to this T shape. So since this one is also chained, we can't have either an L or a T shape because it's already been there once in the chain. It's kind of like we're making charm bracelets and there are no repeats allowed. All of these were forced. So we have an L shape in this chain. Well, if we, so hypothesis that this is not a part of this 4 block, then we got to go this way, can't use this way, and then finally this way. So it kind of fits, but then we've left no room for this to grow. So that can't be right. All right, so if we go this way and this way again, we would still be blocking out this 4, so we can't do that. I think that's as far as we can take that. Well, we could know for sure since, well, we can't know for sure. This might cut off here, and because there's a block over here. That's just barely possible. Well, is that? No, that's not possible here. So hypothesis, if there were a block here, then this would be not done. And then there is enough room. Oops, sorry. Here. Let's just hypothesis color here. This isn't the, I mean, I already worked it out, but so this is where the block would have to go. And the problem now is that there's no way for this thing to be chained. Oh wait, it would be chained to this. Never mind. So that's not actually that bad. Okay. I guess we can't draw any conclusions about that yet. There's only one way for this 4 on the side to grow up. So like if this was blank, then the shape that it's going to make has to look like this. And the problem is there's no 4. There's no room for the 4 on the top. Interesting. We have an L in this chain, so we can't make this an L like that. So it's going to be an S shape, no matter which one we fill in at the end. I guess that's interesting because we can't make this an L or an S shape. That actually eliminates quite a few possibilities for what it can be. We could make an I shape. We could make a T shape, but that's it. Let's examine. I guess that one's not so interesting yet. This one has a lot of space to go, and this one could actually, I thought it would get stopped over here, but it can actually just kind of keep growing down that way. Same with these ones. They're just a little too free for us to draw any conclusions. One might well ask, what chain is this going to be connected to up in the top? If we know that it can't be an L or an S, because it's got to be connected to this chain somehow, which is not totally the case, right? You might be able to, well, it could be a 2x2, a little square, and it could connect to this. It could be a T and connect to this one. I don't think there's a way to make it so that it can diagonally connect outside of this chain, like down to this. Because the only way for it to connect to this, okay, well, this is kind of interesting. I think this is right. Suppose that this were a block, then these can't be shared. We've definitely got to go this way and this way. And this can't be shared. And this can't be shared. So we'd have to make another S in the chain. And this would make 2. That's a violation. Therefore, this block that we drew can't be used. And it's got to go like so. This one's got to extend down here. And at the end of the day, it's either going to be an L or an I. Now, it can't be an L because this chain is all connected out to here. So it's got to be an I. Another interesting hypothesis. What if it were connected to a block up here? We would bring that up this way because it's got to make a block. It can't connect to this one because it's too big. That would be like 6 on a 4. Then it connects either to this one or to this one. But if it connects this way, it's an L in a chain with an L. If it connects this way, it's an S in a chain with an S. So there's no way to connect it. Therefore, this is not a block. And because this one has to be in a chain, this one is a block. Now, I don't think we can have blocks without numbers, right? Shaded areas. Oops. Just want to look at the rules. Right, each of the areas contains exactly one cell with a number. It's still going. So, which block with a number can this reach? There's actually only one answer. It's this one. And if this is not a block, then there's no way for this to reach in less than 5 squares. So this has to be a block. And we don't know where the final thing goes, if it's a T for this side, or an L on this one or this one. We can be sure that this is not a block. And we can be sure that these are all chained together. Now we can know that this one is not an I, because that would interfere with this 4 down here. They'd touch each other. We know that it can't be an L, and we know that it can't be an S. It can't be an L like so. So the only one left is T, I think. So if we put a dot here, then we'd be forced to make an L with all of this. It's in a chain with an L, so there has to be a block here. If we put another one here, we'd have two L's. If we put another one here, we'd have two S's. And so we're forced to put one here. There we go. So there's our L, S on either side, T chain. Then we'd know this one has to connect up to this chain somehow. There's no other chain it can reach. It can only go to this member or this member. And it can't be an L, an S, or a T. So I think that we're stuck making it into a square, an O, I guess. Like if this one weren't used, then we'd be forced to make it a T. So it is used. It doesn't hit this one. This block is done. We have to connect up to the chain. And if we put it up here, we'd have two S's. There we go. Okay, I think that's all justified now. Let's look at this one now. This one has to go, it can go up one this way, but then it has to start going this way. So it definitely goes this way. And then it's forced to go this way. And now we have either an S or an S or an L. Those are the only ways to grow this one. And we've got a couple. This can be a T or an L. And then this one has a lot more freedom. We cannot connect this one because that would put it in the chain that has an S. Okay, that's helpful. One interesting thing, imagine that this were a block. It would have to come out here to come towards a block with a number. And so we'd have this 3-omino with the bend in it. And no matter how we continue, since we're linked to this chain has a circle or an O, an L, an S, and a T. So if we had this, there's no way to continue this shape without making a T up here or a T over here or an S over here. Therefore, this is not block. I mean, I feel like there's considerable space to have these two chains ignore each other. Perhaps this one is a square. This one can't be an I. It can be a T. Oops. And it can be an O. T or O, I think, are available. T could look like this one, and these three. I think that would be a little difficult for this one, actually. It doesn't have that many places to go. I think O is a little difficult for it, too. Because it actually would eliminate the squares that this one needs to grow. So I think O actually doesn't work. So let's just show that. O. Now see what happened here. This one can only make a 3-omino. So this one definitely can't be an O shape. There's nowhere for it to be an I shape. That leaves a T shape. No, wait, the T's happened here. It's the S shape. The S shape that it's got to be. I was reading this wrong. So this one is an L and a T. We've got to do an S shape. we can't connect it to this chain because this one on the end has to be either an L or a T, and they're all accounted for. Maybe we want to sort of scoot it out this way, like keep as far away from me as possible. Let's look at what that does. I think that there's enough room to do this one now. It would avoid touching this one is important. And then we have just enough room to make it into an L shape. This one can't be an L, so it has to be a T. This one can't be an L, so it has to be an S. And then maybe this one could be an O. So this is a solution, I think, that conforms to all the rules. Can we prove it's the only solution? I think that's the challenging part. I think we proved that this has to be an S, right? It can't be an I and it can't be an O. So we could probably eliminate some possibilities by showing that we can't put the S here to this side. There's no way to do this 4 without touching it then at that point. So if this is an S and it's like this, then there are 2 possibilities. We can just draw them both out like so. In this possibility, there's no room for this 4 to go anywhere. In this possibility, we have room to draw this 4, but it has to connect to this chain, which it absolutely can't do. Now there's no room to draw the 4. So having looked at both the possibilities for making this an S, pointed to the left or the right, we find that's not possible. There we go. Now making this an S, it's going to go down to the left or down to the right. We already said we can't go down to the right because that would chain it into this, and we have no way to finish this shape off without doubling up on L or T. So we can't go this way. We have to go this way. All right, and there we go. We can't have this 4 join in on this one. Like they can't connect up. And if we did draw this one, then it would have to grow out to this 4 no matter what, so that it could join a number. All right, there we go. That's our proof. Can't have an L here. Can't have an L here. And this one can't be an L, S, or a T. There's no room for it to be an I. Therefore, it's our last shape, O. There we go. Not a bad little puzzle. All right. The report starts about here. The data flow worked, but exposed that the deterministic lease mechanism is broken for rig agents. The good. It read my branch-only spec from the shared worktree. It caught my real-long solution. It built a working solver, committed on the branch, nothing leaked to main. So that worked. Via an agent workaround. Sanitized token maps to dashes, but the metadata key validator forbids dashes. Boo. Okay. there was a city context prefix mismatch. So instead of working in the rig beads database, it was working in the city beads database. Or is it the other way around? Yeah. I think it was supposed to work in the rig because we're doing rig work trees, but it happened to work in the city one. We missed a formula compiler on a couple of formulas. That one was fixed. Sure, we can fix our bugs in retext. Let me look at what these options are. Do the clean one-liners, restart the puzzle agents, tear down and rerun. If it's green, then that's fine. Review diffs. Nah, I'm good, dog. Choco Banana. We had definitely done this puzzle before. Probably not this exact one. All right. Oh, no, blacken some squares. Blacks are rectangle. Um, two square areas are not orthogonally adjacent. Black cells divide the grid into white areas that are not rectangles. And number indicates the number of cells in the area. It doesn't say we can't have two numbers in the same area, incidentally. I mean, this one's really familiar. Maybe I'm thinking of another one of the chocolate. Yeah. There's like maybe a German chocolate one where you have to make all chocolate rectangles or something like that. Can't have two square areas next to one another. This is a one region, but we don't know whether it's colored black or white yet. That's interesting. So we're going to be drawing borders, and then we're going to be shading as well. This is a 2 region. It can be adjacent to this one if they're different colors. Let's read the rules again carefully. Not look at the solution, really. Okay. Black cells must be rectangles. Square areas are not orthogonally adjacent. Diagonal is okay. And when they say square, they mean a rectangle that's the same size on both height and width. White areas are not rectangular. Okay, well, this is interesting. This one is kind of a special case, right? This is rectangular, but white areas may not be rectangular. Maybe if we take down the opacity a little bit, yeah, there we go. Okay. We can still see the numbers underneath. That might be helpful. This 3 region, I guess it can be a rectangle. It could be a 1x3 rectangle. Dang, I thought I was getting somewhere. This 7 region definitely can't be a rectangle because there's not enough room for a 1x7 rectangle in this grid. So it can't be a black region. It has to be a white region, which I guess we can signify by like underline, maybe? If this is a black region, I guess we could do dots too. Why don't we just do dots? If this is a black region, it needs to be surrounded by a white region. If this were white, then it would be too big. This would be a 3 region. So this is a black region. And there are borders between black and white regions. Do we have to have a number in every region? Or is this legal if we drew a border up here? It doesn't say that. Let's add up some numbers here. We have the numbers 1 through 7. They add to 28. And we have the number, we have 36 in the grid. So we're definitely not going to have the law that every square needs to be in a region with a number in it. Here's an interesting one. This 2 is going to either grow this way and stop and put a border with this 3, or it's going to grow this way and stop and put a border with this 3. So these aren't the same color. This has to be white. Since this can't be rectangular, that's kind of interesting. Okay, let's start with that. If we put a border here, then this white region would be rectangular, so there is no border. If we put a border here, this white region would be rectangular, therefore there is no border. If we joined this white 3 and these white dots, then that would make a region of 4, and this is only a region of 3, so they can't be joined. Therefore, this is a 2 black region, and that completes this rectangular black region. Now this, if we put a border here, this white region would be rectangular, and we can't do that. So we know that this is a 6 region, and we also know it's not going to be a rectangle, because no matter how we expand, we're not going to make a rectangle. We know, because it's adjacent to this 2 size bordered black region, that this stuff is white. And we would know that we can't join these two because they'd be 2 different sizes in the same, and the numbers would be all wrong anyway. Now we've got a region of 5, and there's only one way to expand it, and that's this way. This is interesting because this is a black region that's already a rectangle. It's not plain whether we're supposed to keep expanding it to the right or not. We have a white region here. It can't expand up this way because it would be the wrong size completely. So it's going to expand this way or this way. It would be possible for it to expand this way, and then there'd be a border here, and this would be black. And this would also be black to keep this black region rectangular. Or it could expand up this way, and then this would be black, and this would be black. All right. Now we're talking about how squished together some of this stuff is that's remaining in the puzzle. We know that this white region is going to have to do something screwy, and the most obvious solution to get 7, right, is that it creep over here and then form a region of 7 like this. Maybe we'd have, we need to have about 8 cells that aren't attached to any number to have our solution of 36 cells and 28 numbers accounted for. Okay, just checking a notification. How's the mayor doing, by the way? Still working hard? Are we having get auth issues preventing us from using our formula? That would suck. We were dealing with that yesterday. I might have to fool around with the SSH agent a little bit. Well, let's consider what would happen if 4 was white. I guess it would be not a rectangle. Well, it couldn't. Okay, yeah. Let's start the experiment. Step 1. What if 4 is white? Then this can't be joined right here. And this would be the end. This would be the end of this area right here. And there'd be a border here and here. There'd be a border here. And 4 would definitely have to expand the white either down this way or down this way. 5 would be black. And the only way to make a 5 rectangle is to go 1 by 5 up here. Because there's no other, it's prime, there's no other divisor of 5. And so when we start drawing the 1 by 5 rectangle, we make a non-rectangle. Therefore, it's not possible for 4 to be white. It has to be black. If it's black, it's part of this region. And the only way to keep this a 4 rectangular region is like so. I don't know why it's warning us about adjacent square regions, because the only way to have 2 squares is to have 2 black regions. Oh, just a sec. I did it again. I've been talking to myself for an hour and not unmuted the microphone. So sorry. Dang it. Let me catch you up to speed. We had our mayor working on basically retesting all of our smoke testing using worktree releases for all of our agents. My soapbox is all gone too. I talked briefly about, man, I guess I just need to stop doing this. I can't mute the microphone. I was going to sneeze though, so let me mute it briefly and come back. Still didn't quite get it. Dang. I think what's really weird about this is that I can mute my microphone and still have the sound coming through the monitor. And so monitoring isn't helping that much. I don't know what to do about that. I guess I'll double check. Like, we have got the desktop audio in the audio mixer. I don't know. I'm getting a little confused about the unprofessional nature of my stream. Sorry. Um, okay. We were talking about one-way doors and the expense of having to undo work that has already been deployed. And a lot of the work has been happening in a branch so far. And we're trying to smoke test this work of having agents work inside of a collaborative work tree and then ship their work to main when they're done. And it's been going through various bug tests and smoke tests related to that. Uh, the one way door thing, we were trying to talk about how sometimes it's physically impossible or extremely unworkable to go backwards once you've made a decision like expanding your data model or offering a public API, because customers want to use it forever. And if we don't want to break our customers, then we need to keep everything backwards compatible. That means we need to support whatever data model we have published or whatever API we have published. And so growing those things are very much like one-way door decisions. It's very difficult to unwind them. People start building on top of them, and it becomes this load-bearing piece of infrastructure, not just for you, but for them. And so those are sort of like one-way door decisions in software. One and a half way doors are things that you could unwind, but it would be expensive to do so. So, for instance, we could push all of this new functionality to work against worktrees and that kind of thing. And unwinding that would be expensive. Maybe we'd have records that sort of imply that worktrees were used. Maybe that's gone into a whole bunch of different edits across all of our formulas and agent prompts and so on. And we'd have to take all of that back in a sort of messy way. Um, that's the essence of the soapbox that you now get to hear. All right. So it's still working on that, and we've had some trouble over the last 2 days, like with GitHub auth. So agents should be able to, like, I've given them free reign to commit to the puzzle pack, the rig repository that we set up, a private repository, and to the city repository. They're like, it's like, go nuts, do your own thing. And, we'll have everything in Git if we need to back up or if we need to unwind some change that you made there. We'll have the whole ref log and everything will be fine. All right, there's a Mayor heartbeat. So we fixed bugs 1 and 2 and 3. Yeah, maybe I can figure out this GitHub auth thing kind of on the side. Yeah, we can't do account passwords for Git command line operations. We have an SSH key. Let me see if the SSH key is present on the account. Maybe it needs to be uploaded again. Maybe this is something you have to do periodically. That's kind of weird in my opinion, but it's fine. It's not a biometric or security key. We turned on two-factor, that's fine. SSH and GPG keys. Yeah, there's an SSH key. It's been used in the last week. Troubleshoot common SSH problems. All right. Maybe I'll work this problem in the dark. Just a minute. Okay. And we're going through like, if it helps, if you want to follow along a little bit, we're looking at this. That's the error signature that the agents were getting. I don't think this is... Hi, Rainydan, you successfully authenticated, but GitHub does not provide shell access. That's fine, I think. Connecting to GitHub on port 22. Check, it did do that. The connection was established. The host is known, it matches the host key in known hosts. It did a public key authentication. The server accepted the public key. We've successfully authenticated, but they don't actually provide SSH access to Git, which is fine. All connections, including those made for remote URLs, must be made as the Git user. So if it's trying to connect as me, then it will fail. Permission died, public key. You can verify your connection by doing SSH-T git at github.com. You should see your username. Yep, sure enough. Make sure you have a key that's being used. You can also check that the key is being used. Verified the public key is attached to your account. We did that. They say to make sure SSH agent is running. Sure enough. All right. I think it must be doing something wrong. I think the agent itself must be invoking the Git wrong, perhaps. Okay, back to awareness here. The retest succeeded. We were just watching the wrong keys. I went through the troubleshooting steps on to see if I can find why the Git invocations were not working. Maybe there was a problem with the way it was used. Side issue, but it would be nice if the agents all used the CLI correctly. Okay, and we're back. Okay, we're still choco bananing. Yeah, right. So we figured out this one. That was good. It shares a border with 5. 5's got to be white. Ah, this has to be white on the border of this choco area. We finished our white area. It's not a rectangle. Good. Oh, oops. Now I'm doing the borders of the completed area. That caused a border here too. We definitely have to grow this white area out this way. Note what happened here. We can't have two black areas run into each other because they'll create a non-rectangle. There we go. Same right here. We can't continue this 5 out to here because it'll make a region of size 6. There's the 5 region that's white. This white area is a rectangle if we cut it off right here, so it's got to continue. It's in fact connected to this 7 area. No choice on that one. Notice how these black areas are unnumbered. So almost all the numbers have been accounted for. We need a I guess the point of this 7 area is that say that there is another black on this chocolate right here. Then we have to continue pushing the 7 out this way, and that would be 5 cells, 6 cells, and then we have to go here to get the 7th cell, and that connects it up to this 3, which would make 10. Therefore, this can't be chocolate. Now we've got 5 cells here. We've definitely got to put one here. So if we put the 6th cell here, then there's nowhere for it to expand but here. And then we can't connect these up. There we go. So in our sort of unaccounted for by number areas, we've got 3 white cells with no number, and then we've got 2, 1, 1, 1 with no number. That tracks. Those are the 8 untracked cells. And there's our non-rectangular white area. I enjoyed this puzzle too. I thought it was interesting. We had to think a bit about the borders, and then we had to think a bit about the shapes that were getting created. Hmm. Okay, so it looks like I need to unlock this with SSH add. Maybe that lapses every now and then. SSH add L dash capital E. Then I should be looking at Okay. All right, so I ran the SSH add. I drive a mayor held lease. Oh, sorry, here. Back to Vision again. I did the SSH add, so. Sure, that's fine. Let's not just test it in production. It's fine. I think that this is not leaking anything. Okay. It's spinning plates with me a little bit now, but hopefully it's free to do its thing. Okay, we had a fun chocolate banana, double chocolate. Divide into regions. A region is going to have a black and a white area. They'll have the same form and size, rotated or reflected, the same omino. A number indicates how many cells of one color. A region may contain several cells with numbers, in which case it must all be equal. Okay. Just not look at the solution. Not that I can remember. And I'm not sure what's going on here. I guess this is a sample. All right. So it has to be one of each. So for instance, in this one, we can't have two black cells. We need to have this one white cell. Same here. Now we're not sure which black cell or which white cell is going to pair up with this. We do know from this 4 is a black omino, and there's exactly these 4 that have to be in that omino. It makes an L shape, and now we need a white L shape to pair with it. And, oh, oops. There we go. We should only be drawing borders between black and black, right? And here's the white L shape. There's only one way to make it again. Like so. Oops, I keep drawing that. The border, I keep drawing this one. Shouldn't draw. Because they are in the same region. Now the region of this white one is plain. The region of this 3 is also plain. It has to go like so. And it meets this black 3 omino right there. We've got this black region of 4. And it's got to make a white L shape. There's only one way to do that, connected to this shape. And it looks like so. Here we've got 2 black and white shapes. Here we've got 2 black and 2 white, and a black and white shape. Okay. It could be more complicated. You could see how it could possibly branch in different ways, but this one didn't do that very much. It like really railroaded us to the solution. How's the mayor doing? Did it answer our question about SSH add? Still not usable. The GPG agent. Interesting. I see. You have to configure GPG agent to act as your SSH agent. Okay. It will use the GitHub CLI over HTTPS. All right, so we can sort that later. I don't know exactly what it's, so I have a fairly superficial understanding of how SSH agent works in the first place. Don't know why these shells are pointing at GPG agent. Yeah, maybe I just need to look into that separately. Hopefully no big deal. It's telling me what it wants me to do pretty bad. How do I feel about doing this? I mean, fine, no big deal. I don't know what's going to happen. So once again, for security-minded reasons, let's not just broadcast any auth stuff over the internet. Uh-oh. Did I write that down somewhere? Hopefully this is it. Maybe with no dashes? That sucks. I'm going to type it real slowly, but if this doesn't work, then... Bad passphrase. That sucks. Real slow with no dashes. What else would I have called this? If anything. Nope. Nope. I might have written it down somewhere, but yeah, trying to remember a passphrase is obviously no fun. Really not sure. Let's just close that up and oops. I just want to, yeah. Okay. Let's just get back to reality here. All right. Still working hard. The inventor ignored the protocol. Don't do that. Well, it's okay if it reverts the changes that it messes up when we're testing out this stuff. All right, so we took care of double chocolate. Gosan Fuwari. Oh yeah, we've done this type of puzzle before. It's we've got sort of lead iron balls and balloons. Balloons have to float to the top or to a black cell, which is like a roof, and black cells have to float to the bottom or the black cell, which is like a floor. I don't think we did this exact puzzle before, but we could just do it again. All right. This was pretty fun, as I remember too. And like a really interesting, like I think this is the first puzzle I saw that used gravity, right? Every region has one black ball and one white ball. And we can't have them floating on nothing. So like this can't be a black ball because there'd have to be a black ball underneath it to hit the floor. So it can be nothing, or it can be the white ball. If this were a black ball, we'd have to have a line of black balls all the way to the bottom. Therefore, the black ball is here. And we're not sure about the white ball yet. I guess we're going to use dot for empty and circle for balloon. It's barely possible that we could have a line of black balls stretching down to the bottom. But it's not possible, for instance, we could have a black ball here floating on nothing, a black ball here floating on nothing. A black ball here would be okay, because there could be a black ball down here. But then we'd have a black ball floating on nothing somewhere in here. So none of these work for black ball. That means it has to be right here. And there has to be a black ball underneath it. We definitely can't have a balloon with space on the top. So the balloon's got to be right here. There's the space. And we can't have space on top of this balloon. There's the empty space. That also means we don't have any, this isn't a circle. It has to be a black ball, because we only got two choices. And this has to be a circle. And when it's a black ball, it's black balls all the way down. Like so. If we put the circle on this one over here, then it would have to be circles all the way up. And it's impossible starting even right here. We can't have two circles in one region. We only get to have at most one. We can't have the circle here because it would have error above it. We can't have the circle here because it would definitely have some error above it. We could have it here. Actually, yeah, here's a circle. It's possible to have a circle here. And we need to have a circle here somewhere. This one, we can't have a circle down here because it have air above it. And we know circles would float through the air. And similarly here, we can't have air above this circle. All right, so far so good. We can't locate the black ball over here because there's air below it. Definitely not here. Here or here. It's got to be right here. We can't have the circle on the left side. And there can't be air above it, so it's got to be right here. We can't have a circle here because there are two lines in a row where we'd have to have more circles. We can't have the circle right here because there's two lines here that can't all be circles. There's the circle. This can't be a circle because it would have air above it. Same. All right. We definitely can't put an X here because we'd have to have a line of X's down to the floor. We can't get 3 X's in a row right here. It's got to be on this column, and that means it's got to be down to bottom. Because there can't be any air or balloons below this X. And similarly right here, we got to have a line of X's down to the floor. We can't have the circle here. Got to be here or here. This circle can't have air above it. Can't have air above it. There we go. We can't have an X on the top with air below it. There's got to be a line of X's down to the floor. We got to have the circle float to the top of this region. We can't have a circle here. It would float through air. We got to put our X below our air. We got to have X's down to the floor. And we can have the circle not under the air, but under this other circle would be fine. There we go. I find this fun, interesting, even if it was a little fast. Okay, how are we doing? Let's try another test. I'm not sure if it's telling me that this approach is unworkable, or if it's just telling me that something was messed up on this trial. But yeah, we do want to revert these changes that didn't follow the process. Gokigen naname. Slalom or slant. We're very familiar with this one from Simon Tatham. Anything that's in Simon Tatham, we've probably played 1,000 times. Yeah, the idea is that we get slanted lines. We need one in every single square. And we have to get the number of edges coming into each bubble correct. So our only choices are backslash or forward slash. And if we stick a forward slash into a 0, then we violated its edge incidence number. And we can go through the whole puzzle like this. The other rule is that we can't make circuits. So like, for instance, say that we had these two ones connected. In order to keep the edge incidence numbers right, we have to avoid them with all the surrounding edges. But now we've created a circuit. So actually, it was not possible to connect up these two ones. For a very similar reason, here we've got two ones adjacent to one another. If we put an edge into this one from the top, from outside of the two ones, then we're going to violate the edge incidence of this bottom one. So they have to sort of make a hat. And the similar thing holds on the bottom. We have to make hats. And it happens even on the side, like so. We sort of have to make one hat so that we don't put two edges into the one on the edge, on the side of the grid. This one in the corner, there's only one way to do that. And the adjacent ones, I'll have to use the same orientation of line. Here we have nowhere left to put this 2. This 3 is also like so. This 2 was completed. This 1 was completed. This 2, there's only one way to do it. This 2, the same. We had to do this way so that we didn't form circuit and so that we got the edge incidence right. Here's another place where we need some hats. We need 2 into this. We can't make a little square here, so we've got to make that edge like so. I wouldn't say this is the most interesting grid that we could be demonstrating this puzzle on, but it doesn't get much harder than this. Basically, You might get some longer, bigger circuits being formed in a bigger grid. That it would be more difficult to make these inferences on a piece of paper for sure. So we can't do this one. We got to do this one. There you go. And that's the end of slant. Oh, so yeah, this the same. It's the same thing. We won't like do another one of those puzzles. Hashiwo Kakado bridges. We're super familiar with. Again, Simon Tatham. Here they are. Here's a random one. We can have up to 2 bridges in any cardinal direction. We can't violate the edge incidence of anything that's already been satisfied, like this one has 1 bridge, so it's done. And we can't cross lines, which sometimes is relevant. In this particular puzzle, I wouldn't say super relevant. There you go. It's a small one. Bigger ones are bigger. Itori we're familiar with, a solitaire variant of reversible. Place black stones onto empty cells, and you keep capturing some white stones. A number on a white stone indicates in which move this stone must be captured. It's kind of wild, but it's like, are we going to capture all of the stones? No, it doesn't. Okay, yeah, we are. 1, 2. This would be black then. 3. These would be black then. 4, 5. And maybe the problem is, you know that to capture this one, there's only one way to do that. You've got to have black stones here and here, but you don't know which numbers they are yet. And the only way to put a well, yeah. You might be able to do it faster. Hmm. Let's look at it for a minute, but this isn't my favorite at all. It's like, it's sort of like, how did you get to this chess position? If you really love Othello, Reversi, I guess. And the rule is we're going to capture everything, right? With each move, you must capture. We're also kind of scribbling all over our grid if we do this, right? So yeah, observe that there's no way to capture this stone, which is on the edge, except from these corners. So this is definitely going to be a thing at some point. We could capture it on move 2, right? 1, 2. Look what would happen if we didn't have this number. 3, 4. We've captured all of the stones because we went this way, this way, this way, this way. But for some reason we have to delay and we have to capture another stone. Hmm. along the way. One thing that's interesting if we capture this stone early is that we can't put a stone down here because that's sort of how uh, we sort of need two moves to get through here, and we've got to have a black on one end and white through the middle to put this corner stone down. I guess we'd be evaluating. So there's a world in which, so there are only two captures available on the board. So we could try this world, where this is number one. Then we'd have, I guess what's wrong with number one is that there's just no way to approach these stones anymore to capture one of them, sort of set up one of these two corner moves in a capture. So we'd be forced to take this one as number one. Then this would be black. Then we have a bunch of other capturing moves to evaluate, like we can't do this one because that would capture this one not on move 5. We would have do this one again, which again still messes us up for this. Or I guess we'd be forced to do this one. So that would cause, this would be number 2, I guess. So these would both be black at this point. We can get over here. With a capture 3, 4, and then 5. I mean, this is probably the solution. But it doesn't feel like a super like incremental type puzzle, right? It's like we're finding our way through the decision tree and there's only one real path through it. Yeah. And this delaying move is just kind of weird. It's weird that we're doing a suboptimal thing because we have to capture this one on number 5. So yeah, maybe I just didn't like this example, but not a favorite. Firefly beam. Let's save it. We might finish all these today. Connect all circles following the grid lines. It starts in a dot on a circle and ends in the same or another circle on a position without a dot. Follows the grid lines. A same or another circle without a dot. So they're allowed to loop back or to another one. We can't go from dot to dot. I guess because each dot is a firefly that is flying to a different location. Okay. How often the path turns 90 before reaching the target circle? Unspecified. A grid dot must be visited most once, and we must form a connected graph. We don't have anything about crossing. Can paths cross? Hmm. How many 90-degree turns there are? I think we'd want to start with 0, right? Let's think a little bit about orientations. If this one's going to come out this way, I mean, I think that's true, right? Maybe this implies that the paths can't cross each other because we're forming a connected graph. Okay, it's doing its thing. All dots must be used. We got that? At most once. Starting in the dot of this circle. It sure looks like they all have to be used. Now the 2 ones. Let's pretend that we know that that's true. It's not necessarily so that this one has to turn left. It has choices. We could do all of this at least. Look what it means to turn 90 degrees twice. It means that you're going to end up going north and you're going to hit a circle. But you're not going from a dot to a dot. That would cause 2 fireflies to like collide in midair. So this one actually can't go this way. It's got to go like so. And this one has to go like so. Similarly, these ones have to kind of trail away from each other. Now there's no law that says, so this one is done turning actually. It's got to go straight ahead to its destination. There was no choice for that. It's sort of like musical chairs, what they're doing here. This one's allowed to land. A grid dot must be visited at most once. All circles must form a connected graph. Since there's a dot on every circle, does that imply that we have to visit every circle exactly once? I think it does. Yeah, because if we visited some circle twice, then we have to visit another circle 0 times. And we got exactly as many paths as we do circles. We're not sure if we go straight. Oh, we can't go straight because it would end and we have to turn. So we have to turn. We can't go. Oh, well, this circle hasn't been visited yet. Don't we have to do this? We definitely can't join something that would turn like 1, 2, 3, 4 times to something that has to join exactly 2 times. I think we're reasoning through this correctly, but can't have 2 dots go the same way. This one can't go forward, so it's done turning, and there it goes. This one has to turn 3 times. Definitely can't go left. Can't go forward. Gotta turn now. Can't go up because it's dot to dot. Can't go right, dot to dot. It's gotta go down 2. It can turn either right or left. I think there's no other way for this circle to be visited than for this to go this way. This one can't visit that way. No other way for this to go than visit this one. This one can't go dot to dot. That's to continue because it's made its 2 turns. This is the only way for this one to get visited. They can't visit themselves because then they wouldn't be a fully connected graph. I haven't taken advantage of that yet, but we're not sure if this one goes this way or keeps going. This one could go straight. We can't do dot dot dot. There we go. So it has to continue. These can't form a cycle either because they all have to be fully connected. So something has to come in this way. This has turned once, twice. This one doesn't go this way and it doesn't branch there. This continues on to its destination. That seems wrong. Something's off there. We've got this cycle here. Can't be right. What did I do wrong? I mean, this would be pretty deep in the puzzle, right? Can't go this way, can't go this way. It has to go this way. This one has to continue because it can't go to either of these. This one can't loop back. I think this is the only way in. This could look like this and this. Let's just assume it is because we think we've done it wrong anyway, right? If we know this can't loop back, then it should go like so. This one would have to continue because it's had its 2 turns. This is a problem. Yeah. So I think if it were like so, I mean, this has too many turns, right? Left, da, da. So I made some mistake. But I'm not sure the nature of that mistake. And let's start over. Okay. So I think these are all hard forced right here. And we also think that the ones in the corners have to go like so. Then we believe that we can't have two dots joined together. So we have to go like so. And this one can't join this next dot, so it has to go like so. And it can't join on itself, because then we can't have a fully connected graph. So far, so good. This one won't go to itself. But maybe it ends right here. Or it continues, hard to say. Okay, this path can't go here because it's forking. It's got to go this way. And this one can't go that way. It's got to go into the corner. And then it continues because it's had two turns, and it can't turn anymore until it reaches its destination. This one can't go here for a branch, and it can't go straight. It needs to turn. It can't continue straight because it'll be dot to dot. And it can't turn south because then it's out of turns and it will make a dot to dot path. So it's got to go north. I think no choices about that stuff. We've got to have something come in to this right here, and this has to turn. I don't feel like I'm adding a whole lot of rigor here, but maybe the X's are helping me or somebody. This one needs to turn 3 times. This one needs to turn 2 times. Needs to turn. I guess that means that we've got to come in on this edge. There's no other way into this one but through here. This one's turned twice. It's got to continue on to its destination, right? Lily pads? I don't know. Two turns and no choices. I guess something's got to come into this pad like so and so. We can't make a cycle. It can't come from this one because that's only 2 turns. Maybe just being slightly more careful is working to our advantage here. We've got to come into this one. That's this here. It's sort of like a Slitherlink loop, actually, now that I think about it. It's like a Slitherlink loop where there are certain checkpoints and you have to turn the loop at those checkpoints. It is a Slitherlink loop, right? There's gotta be an exact circuit through. So we know that this can't be branching either. It's happened again. We've made our circle. What's going on? This makes it not fully connected. I felt like we were being pretty careful. We can't do dot to dot. And then this one has only turned twice. Maybe we're allowed to cross paths. Maybe that's the only thing I can think of right now. Something went wrong right here. All right, let's look at the solution a little bit. Oh, this forking was allowed. How is that possible? So on this one, we didn't have to make a loop. We were allowed to have a starting path if you want. Okay, so that was an assumption that we weren't allowed to make, really. Let's look at the rules again. I don't know why I've had so much trouble. Connect all circles by paths. A grid dot must be visited by a path at most once. But we don't say that every circle has to be a destination. I guess that's the thing that we're not doing. All right. With that distinction in mind, we can come back and do that. Boo. I think this is going to be a lessons learned time. Now, it's good that it's trying to work on its backlog, but oh, here we are. Otaru Bimu, Firefly Beam. So they actually have it down here. Okay, let's try to solve this for the third time, not feeling like we have to resolve the, like every circle must be visited. That is a painful misreading of the rules. This is correct though. Can't connect dot to dot. And we might be able to put in a cycle. So I don't think that we're as sure that we couldn't do this line. because some other one could do it. Like we're allowed to do that at least once. Can't do dot to dot, so this is right. There wasn't path branching. I mean, I think that we can infer that this one doesn't follow this path, that these ones don't collide. I don't see how the paths can form a graph if we have two edges that sort of are half of one edge and half of another, that have two starting nodes and one ending node. Okay, so this is helping us out a little bit. Can't turn, oops. There we go. Let's believe that this is a rule, that we can't have two forking edges at the same grid point. That would forbid this. It would forbid this. One. This one can't be used because it would be a dot to dot edge. This one would also be a dot to dot edge. This would be not enough turns. And we haven't eliminated come back to self. That is a possibility. Can't do this dot to dot edge or this dot to dot edge. We have to do this one and keep going because we're out of turns. This goes here. We're not sure if this loops back east or west. Can't do this dot to dot edge. So this one continues because it's used up its turns. This one has to go this way, no dot to dot edge, turn. And this one has to go all the way down. No forking edge means we have got to go this way. No dot to dot edge means we got to go like so. So there's the loop again, but we're not as wigged now. We think that this might be legal. This is kind of interesting what happened here. Since there's no forking edges, we can actually see that there is an origin right here. No forking edges here. We're just drawing no forking edges. So the only edge that's left to connect this to the rest, we've looked at every other single edge, is this one. Now these are connected again. We fulfilled this. No forking edges. I know how that sounds, kind of funny. All right. Now this thing has to be connected to the rest. So one of these edges has to come in. We can't make it this one because it has to turn. And so this subgraph right here only has one exit, and it's right here. I sort of wish the no forking edges rule was more obvious in the rules. These would be cut off if we didn't go this way. Like this end here. And similarly, this subgraph would get cut off if we didn't connect it up. And here. All right, so this subgraph now extends down to here. And this subgraph extends out to here. So this has to be connected. If this looped back, then it would cut off the subgraph. Oh, and this turned twice. It has to keep going straight. No more turns. I mean, it seems relatively obvious now that there aren't too many other ways to go. If this looped back, it would be... We basically need to be able to join these two subgraphs together. Well, say 3. And we've only got 2 paths left to do it. We've got this little subgraph right here. We've got the one that ends here, and we've got the one that ends here. So we could kind of prove that, like, if we use one of these on a loopback, then we'll have 3 fragments and only one edge left to join them all, and that's not possible. This would be dot to dot. These two are joined, and now we need to join our last subgraph in. Okay. So I think that's our answer. We start here, kind of castle our way around, down and up. Oops. Castle our way around, go up, and then we castle our way to this loop. Let's look at their answer. Start here, way up, castle our way around, down and up, way down, up, and then this loop. Yeah. A grid dot must be visited by a path at most once. Does that mean an intersection? Or is it talking about a dot on a circle? No, a grid dot. That means a coordinate, I guess. Does that mean no forking? It's sort of, that's kind of what it says to me. We needed that rule. I think as long as the rules are clear that this could be a rule fun puzzle. I started to get the hang of it. All right, let's see what we're saying here. The inventor is uncontrollable. We should fix the inventor. I think this is really funny. It's like this is from the manager to the skip level. I have this problem employee. Let's try to draw some lessons from this episode that are generically useful for directing the specialist, the department agents. We're doing it. We're training the manager. Okay. So this is like a Ken, but the only symbol available is multiplication. It's like a subset of Ken. Ken is like I apply a mathematical here we go. I apply a mathematical formula to all of the numbers in a region. We're also doing Sudoku and unique columns and rows. And whatever the result is of the mathematical operation, that's got to be done by the numbers in here. And so for multiplication and addition, you can have more than two. For subtraction and division, you got to have exactly two. The order is not determined, but division of three numbers is not exactly well defined, nor is subtraction of three numbers. All right, let's get to like pencil size. There we go. So this one is 3 or 5. This one is also 3 or 5. These are the only ways you can multiply two numbers from 1 to 5, the grid size, to get 15. Here we've got 2 or 3, 2 or 3. If the grid were bigger, we could also think about 1 and 6. Because 2 and 3 have been used, we can't use 3 down here. This is going to be 5. And erase. Because that 5 was used, this has got to be a 3. This one's going to be 1 times 3. Only way to do that. We can't use a 3 over here, so this one's got to be 2, 3. 1 times 4, we don't know which order they're in. 2 times 5, 10. This has got to be 4, 1. A single square, it's got to be itself. 2. These numbers have to multiply to 20. That's 5 times 4. This is 4 or 5 on the row. The uniqueness. 4 times 1. 2 times 3. All right. It's probably time for me to retire for lunch. Anyway, there's factors. They could be harder if there are more options for all of these multiplications. Okay. Lessons from coaching the problem employee. Ah, okay. So the problem was we had a worker that had been prompted in a certain way, and then it wasn't on the new system. We have to enforce some boundaries. I would love to go through all this. Let's start here when we resume. I think it's really quite fascinating. Anyway, I hope you're enjoying us writing our puzzle company from scratch. And hopefully, we'll be able to get onto this system today and then maybe actually use it to do some stuff. So, hope you have a good one. See you later.